Welcome to our Group 3 presentation. Our topics are exact differential equations, linear equations of first order, and equations reducible to linear equations. Here are our learning objectives. By the end of this lesson, the students will be able to: first, define exact differential equations, linear equations of first order, equations reducible to linear equations, their purposes, and the specific formulas used. Second, explain the process of solving exact differential equations, linear equations of first order, equations reducible to linear equations with correct reasoning. Third, solve exact differential equations, linear equations of first order, equations reducible to linear equations by following the process and with accurate analysis. And the last but not the least, organize the lesson based on their own understanding and inquiries. A differential equation is any equation which contains derivatives, either ordinary derivatives or partial derivatives. The order of a differential equation is the largest derivative present in the differential equation. In the differential equations, 3 is the first-order differential equations. 4, 5, 6, 8, and 9 are second-order differential equations. 10 is a third-order differential equation, and 7 is a fourth-order differential equation. Note that the order does not depend on whether or not you've got ordinary or partial derivatives in the differential equation. And now, let's have the differential equations and concepts of first-order differential equations, specifically exact differential equations, linear equations of first order, and equations reducible to linear equations. And now, to discuss about the exact differential equations, I will give the floor to Ms. Maria Virginia Butcon.
Good day everyone. At this moment, we will talk about exact differential equations. Now, even though the variables are not separable in a given differential equation, certain integral combinations may occur that make it possible to solve the equations readily. Now, I will present to you a few of the simpler integral combinations. So, it was presented in the screen. So, we have 5 integrable combinations. Okay. So, the differential equation in the form the function of p of xy dx plus the function of q xy dy equals 0 is said to be an exact differential equation if there exists a function of f of two variables x and y having continuous partial derivative such that the exact differential equation definition is separated as the function of ux of xy is equal to the function of p xy, and the function of uy of xy is equal to the function of q x and y, and its solution is the function u of xy is equal to c, where c is an arbitrary constant.
Example for exact differential equations. Find the solution for the differential equation 2xy minus sine x times dx plus x squared minus cosine y times dy equals 0. So first, check this equation for exactness. Let aq over ax is equals to a over ax times x squared minus cosine y equals 2x, and ap over ay is equals to a over ay times 2xy minus sine x equals 2x. So let us also check this equation for exactness if it satisfies the condition aq over ax is equals to ap over ay. From the system of two equations, find the functions u of x and y. Let au over ax is equals to 2xy minus sine x, which is our first equation, and au over ay is equals to x squared minus cosine y, which is our second equation. So by integrating the first equation with respect to the variable x, we get u of x and y is equals to integrate 2 of x y minus sine x dx is equals to x squared plus cosine x plus the golden ratio multiplied by y. Substituting the above equation in equation 2, it becomes au over ay is equals to a over ay times x squared plus cosine y plus the golden ratio times y is equals to x squared minus cosine y, which is our equation 2. It becomes x squared plus the golden ratio multiplied to y is equals to x squared minus cosine y. And we get golden ratio multiplied by y, or 2y is equals to negative cosine y. Hence, the golden ratio multiplied to y is equals to integrate negative cosine y dy is equals to negative sine y. So the function u of x and y, xy becomes u of x and y is equals to x squared y plus cosine x minus sine y. So therefore, the general solution for the given differential equation, which is the 2xy minus sine x dx plus x squared minus cosine y dy is equals 0, is x squared y plus cosine x minus sine y is equals to C, which is the general solution.
Hello everyone, I am Julian Herbalde and I'm going to give the definition of linear equations of first order. A first order differential equation is said to be linear if it can be expressed in the form where p and q are functions of x. So, if the function f is a linear expression in y, then the first order differential equation y prime is equal to f of x and y is a linear equation. That is, the equation is linear and the function f takes the form f of x and y is equal to p of x times y plus q of x. Since the linear equation is y is equal to mx plus b, where p and q are continuous functions on some interval I. Differential equations that are not linear are called nonlinear equations. So consider the first order differential equation y prime is equal to f of x and y is a linear equation, and it can be written in the form y prime plus a of x times y is equal to f of x, where p of x and q of x are the functions of x, which are the continuous functions. If p of x or q of x is equal to 0, the differential equation is reduced to the variable separable form. It is easy to solve when the differential equations are in variable separable form. So that is all for the definition of linear equations of first order.
So hello and good day everyone. I am Cherry Luca Iling, and now let's talk about the linear equations of first order solutions. So we will talk about the first order differential equation solutions. Usually, there are two methods considered to solve the linear differential equation of first order. First method is using integrating factor. The second method is the method of variation of constant. So in integrating factor, if a linear differential equation is written in the standard form, y prime plus a of x times y equals 0, then the integrating factor is defined by the formula u of x equals exp times the integral of a of x times dx. Multiplying the integrating factor u of x on the left side of the equation, that converts the left side into the derivative of the product y of x times u of x. So, the general solution of the differential equation is expressed as follows. We have y equals the integral of u of x, f of x, dx plus c over u of x, where c is an arbitrary constant. And that's all for the linear equations of first order.
Now, here is an examples of linear equations of first order. We need to solve the equation of y prime minus y minus x e to the power of x equals 0. So in this way, we can apply the different concepts and properties of the linear equations of first order. So based on what the steps in solving we need to apply in this equation. So let's go. Of course, we need to rewrite the given equation, and this equation becomes y prime minus y equals x e to the power of x. So using the integrating factor, it becomes the u of x. So the u of x is equals to e to the power of integral of negative 1 dx. So this becomes e to the power of negative x if ato siyang i-evaluate ang iyang integral using the integrating factor. After that, we transform the integrating factor. So if we have the value of the integrating factors, we just substitute to our general solution of the linear equation. Therefore, the general solution of this linear equation is this one. So we have here the y of x. The y of x is equals to e to the power of x, x squared over 2 plus c. C is an arbitrary constant. As you can see here, the general solution in the steps that is presented is the integration of the u of x, f of x dx plus c over the u of x. Then, ato na siyang substitute kung sa value sa u of x sa itong gisolve sa integrating factors, e to the power of negative x. So, sa ato ang equation, x e to the power of x dx plus c. Mahimo na dahil copy na dahil ng e. Ang denominator is u of x. So, ang sa value ni u of x, may butan na to, which is e to the power of negative x. So, evaluate na to sa iyang integral sa babaw. Of course, ang integral sa e to the power of x, x e to the power of x dx plus c is equals to x, the integration of x dx plus c over e to the power of x, negative x, rather. So, substituting or applying the integrating procedure, we have here the e to the power of x. So, the answer of the integral of x dx plus c is x squared over 2 plus c. So, this is the final answer.
So hi everyone, my name is Maylene Arbar-Bulas, and for now, let us talk about the equations reducible to linear equations. So for today, I will be showing to you the definition. So in mathematics, an equation is a mathematical statement stating that the value of two mathematical expressions is equal. An equation can be classified as linear, quadratic, cubic, and others. So based on the degree of the variables. So a linear equation is an equation with degree 1.1. The equations reducible to the linear form is defined as the process of converting nonlinear equations to linear equations. So what is reducing equation? So it is the process of converting nonlinear equations to linear equations, because not all equations are provided plainly and straightforwardly. Splitting them down to solve them is necessary. So on both sides, solving these equations requires various mathematical operations such as cross multiplication, division, addition, subtraction, and others. So it helps in the conversion of complex equations to their linear forms. So following this change, determining the value of the variables becomes simple.
So hello and good day everyone, and now I will discuss or will be dealing with the steps in solving equations reducible to linear equations. So we have the 4 simple and easy steps in solving this type of equations. We must go then. Steps for reducing equations to linear form. Suppose we are given an equations of the form ax plus b over bx plus q is equals to c over d. So we let x as the variable and letters a, b, c, d, p, and q are the constants. We will then follow these steps to solve such equations. So we have the 4 simple and easy steps. Step 1, or the first step, we can see that the given equation is a non-linear equation which we cannot resolve directly. So in this problem, we must first use the cross multiplication method to simplify the following problem. Step 2. After cross multiplications, then it means that the denominator on the left hand side is multiplied by the numerator on the right hand side. Step 3. To open the brackets, we must use the distributive law. And for the last step, at the step 4, we will bring all the variables to one side of the equation on the left hand side and the constants to the right hand side and solve the variables value.
Hi, this is me, Maria Luisa Dilubusbog, and I will show you an example of a differential equation that can be reducible into its linear form. Let's have an example. So we are given with an example of dy over dx plus x sine 2y is equals to x cubed cosine squared y. Okay, so in the equation, dy over dx plus x sine 2y is equals to x cubed cosine squared y. Let us multiply 1 over cosine squared y so that only q is left on the right side. So we have now 1 over cosine squared y times the quantity of dy over dx plus x sine 2y is equals to x cubed. Then let's distribute 1 over cosine squared y to the quantity of dy over dx plus 2 plus x sine 2y. So we have 1 over cosine squared y dy over dx plus x sine 2y over cosine squared y is equals to x cubed. Recall that 1 over cosine squared y, by the fundamental identities, it is equals to secant squared y. So we have now secant squared y dy over dx plus x sine 2y over cosine squared y is equals to x cubed. And again, recall that sine 2y is equals to 2 sine y cosine y by the double angle formulas. So we have now secant squared y dy over dx plus x times 2 sine y cosine y over cosine squared y is equals to x cubed. As we could see, we could divide 2 sine y cosine y with cosine squared y is equals to x cubed. So we have now secant squared y dy over dx plus x 2 sine y over cosine y is equals to x cubed. Then recall that sine y over cosine y is equals to tangent y. So we have secant squared y dy over dx plus 2 tangent y times x is equals to x cubed. Now with this equation, let us now reduce this to linear form by putting tangent y is equals to b. So secant squared y dy over dx is equals to dv over dx. Now become dv over dx plus 2v times x is equals to x cubed. Recall the linear form, which is dy over dx plus by is equals to q. In this equation, dv over dx plus 2v times x is equals to x cubed. P is equals to 2x, Q is equals to x cubed, and y is equals to v. Therefore, the linear form of the equation is dv over dx plus 2x times v is equals to x cubed.